Well, hello again, guys and girls. Here we record the recitation lab for week 13. So here's the outline. We'll talk about sequences, series, and convergence, which correspond mainly to sections 9.1 and 9.2. And we'll try to cover 5 examples in this presentation. So here we go. So first of all, we start by a sequence that is defined as an equals 1 minus n over n squared. And we'd like to find the values of an when n equals 1, 2, 3, 4. For this, we upload the file of this week's presentation, which is week 13 presentation. And here we will use a for loop to print the values of an. In our for loop, as you see on this right side, for n in the range from 1 to 5, we define an, which is 1 minus n divided by n squared. We'll print n, we'll print an. And here is the display of our sequence terms. Here is the Jupyter Notebook file. This is the sequence term, an equals 1 minus n over n squared. Here is the for loop, and here is the display. Okay, hopefully everything is clear. That's very easy. Example 2, we have again a sequence such that an is equal to 1 minus 2n over 1 plus 2n squared. And we'd like to see if this sequence converges or diverges. So what we'll do, here we use the limit command. So we use the limit function from SymPy as well as the infinity, which is the double O. So you have to recall this. If you want to call infinity within the limit command, don't forget just that's a double O without space between, of course, the O's. So from SymPy, we import everything using the star. We'll define n as a symbol, which is integer and positive. And we'll define a index n as 1 minus 2 times n, all divided by 1 plus 2 n squared. And we'll display the value of an, of course, the expression of n. And we'll define L as the limit when n of an when n goes to infinity. So this is how the command limit works. And we'll finally display L. And you see that this limit goes to 0. Here is the Jupyter Notebook, the importation of the whole environment of SymPy, n as an integer, positive, an as 1 minus 2, and all divided by 1 plus 2n squared. And here is the display of an. Here is the limit command, the limit of an when n goes to infinity. You see, that's a double O. And we'll display it. The third example, we'll talk again about a sequence. Here we have a different definition. We have a1, which is equal to 2, and an plus 1 equals to 72 over 1 plus an, which is convergent. So we'd like to find the limit of this sequence. To do that, we need to solve this equation. 72 over 1 plus L equals L. Why we are solving this, you might have seen it already in the lecture part. If this sequence converges, so the n plus 1 term converges to the value L, and also an converges to L, so we'll have an plus 1 equals an, or again 72 over 1 plus n equals to L. Okay, so if we try to solve this equation, we get this form, L squared plus L minus 72 to 0. So here again, we retrieve this. We've seen it at the beginning of the semester, how to solve these equations. We define L as a symbol. The equation as D, which is L squared plus L minus 72. And we'll solve for D equal to 0, of course. So when we set S as the solution, we get by the solve command of T. Of course, S would be a list of solutions, and here, of course, we have 2 solutions, minus 9 and 8. Okay, so it could be convergent towards minus 9 and 8. Both solutions seem to be acceptable, but since the first term seems to be equal to 2, okay, and one might say that A2 would be equal to 72 over 1 plus 2, which is what? 72 over 1 plus 2 is 72 divided by 3, which is 24, it seems that the sequence can only take positive terms, so we'll only accept 8. Okay, that closes the debate on whether or not -9 could be accepted because of the initial term, which is a1 equal to 2. Okay, for example 4, we'll talk about series now. So given this series, which is 2 plus 2 over 3 plus 2 over 9 plus 2 divided by 3 to the power n minus 1, and we'd like to find its sum s. One can see that this series is geometric. The initial term, or the first term, is a equal to 2, and the ratio or the reason is equal to 1 over 3. So we say that r is equal to 1 over 3. That's easy to check. And since the absolute value of r is equal to 1 over 3, which is less than 1, we conclude that this geometric series should be convergent. And we know that this converges to what? To a over 1 minus r, when the number of terms goes to infinity. So here we get the importation of the whole environment sim pi, the initial term, which is a equal to 2. We'll define r as the rational 1 over 3, and s, which is the limit, would be a divided by 1 minus r, and just display value of s. That's it. Okay, so we'll see the Jupyter part. For the Jupyter part, we'll see again example 3, because we didn't see it with the Jupyter notebook. This is the previous example, a1 equal to 2, an plus 1 equals 7 to 2 over 1 plus an. We defined L as a symbol. We solved the equation L squared plus L minus 72. How did we solve this? First of all, we defined this polynomial term or second degree term as d, and we solved for d to 0, and here are the two solutions. Of course, we should only accept the positive one because of the initial value a1. The example 4, here we have the given series, the initial term, the rational 1 over 3, which is our r, and s as a divided by 1 minus r. And here is the value of s. Okay, the last example, we will have this series, which is the sum from k equal to 1 to infinity of 4 divided by 4 minus 3, 4n minus 3 times 4n plus 1. You could observe that this seems to be a telescoping series. So to do this, we use the function apart. Function apart here, or the command apart from SimPy, which performs a partial fraction decomposition of a rational function. So what should we do? We import the whole environment. We define n as a symbol, and we write an as 4 divided by 4 times n minus 3 times 4n plus 1. So that's the display of an, and we'll apply a part here to an. And you see that that is displayed as an1 or n1. So answer 1 or an1 is minus 1 over 4n plus 1 plus 1 over 4 minus 4n minus 3. You see, this already saves a lot of time. Okay, if you want to do it by hand, let's check it out. You can write it as a telescoping series. Here, if you start by the first term, when you decompose it, you're going to have 1 minus 1 over 5, and the next term is going to be 1 over 5 minus 1 over n. So the 1 over 5 goes, and you can see that what is left after you sum up is just the first term, which is 1, and the last one, which is minus 1 over 4n plus 1. So you can already write it as 1 minus 1 over 4n plus 1. Okay, so that's the decomposition part. Now, what should we do? We take this last part and we will perform using a sum of expressions. So we'll define k as a symbol, and ak would be a substitution of n by k into an. What is an? An was the initial value here we had before. So we'll sum up the ak's from k equal to 1 to n, and we'll ask it to do it. So that's what we get. We get 4n over 4n plus 1. Okay. So what does this do? So the sum did exactly what we got with the telescopic or the apart decomposition or with the mathematic decomposition here. Okay, and it seems here then when we replace we use the limit on as the sum, the limit of what? The limit when n goes to infinity. Of course, it's going to be 1 because we have 4n divided by 4n plus 1. The two terms up and down are of the same degree. And here we have 4/4, the ratio of the two constants equal to 1. So the series converges to 1. Thank you very much for following. This closes the last recitation for week 13. And wish you good luck and my sincere wishes to have the best grades. Thank you very much and goodbye.